Hello! In this video we'll talk about the single cycle RISC-V processor and in particular implement the data path for the load word instruction. So we're going to break our processor into a data path that operates mostly on 32-bit words, the machine word size for our computer, and then a controller that receives the instruction and based on that sends back control signals to tell the data path what to do. So let's begin by designing the data path, and as we're doing it, we're going to build up the capability to handle various instructions. So imagine the following program that we'll use as an example to visualize what's taking place in the data path. This program, let's say, starts at address 1000 in memory, and it begins with a load word. So load x6 from some offset relative to x9. This is an I-type instruction for load word. So this is the op for the load word. Its source is R9. The immediate is -4. The destination register is R6. And F3 together with the op determined that it was a load word. And the machine language value for this load word was FFC4A303. Next we'll look at a store word instruction. That's an S-type instruction. And then an OR instruction, which is an R-type instruction. And then a branch on equal, a B-type instruction. And once we can run all of these, we're able to do all the interesting things in a basic program. So we're going to begin again with this load word instruction. Load word x6 from -4 parentheses x9, where x6 was the destination register, -4 was the immediate, x9 is the source register, and the op and func together make load word. So let's begin with the architectural state. Remember, we had the program counter, the instruction memory, the register file, and the data memory. And let's start by connecting the program counter to the address input of the instruction memory. So the program counter was at 1000 right here, and we'll hook that to the address of the instruction memory, and we read out from the instruction memory the machine language for the current instruction, which was FFC4A303, the load. And that's this value here on the instruction bus. Next, based on that instruction, we need to read the source registers. For load word, there's just one source register, x9. So we take that instruction field, and we'll look at the RS1 field, bits 19 through 15 of the instruction, which happen to have the value 9 because the source register was x9. We'll go into the register file, read out the value of x9, which suppose happens to be 2004. Now the load word also needs an immediate offset, so we take some more bits of the instruction. Bits 31 through 20 contain the immediate for load word. And those are a bunch of 1s and then 00, which in hexadecimal is FFC. Recall that we need to extend that immediate to be 32 bits long instead of 12. So we'll add a new block of hardware called a sign extender that will take in a smaller number of bits and put out a 32-bit word. Let's call that extended value IMMEXT. And so extending FFC to 32 bits is FFFFFFFC. Bunch of leading 1s and then 2 zeros. So now we have the two sources for the load, 2004 and -4. The next step for load is to add the base address to the offset. So since we're going to be able to need to do a bunch of different kinds of arithmetic, let's put on a general arithmetic logic unit instead of just a single purpose adder. The ALU will take the two sources, source A from the register file and source B with the immediate, and it should add them. So let's provide an ALU control wire to say what the ALU should do. If we think back to chapter 5 where we defined the ALU, the code 010 meant add. So then the ALU will put out a result. That's the sum of 2004 and -4 is 2000. That's the address that we want to load from. Next, we need to read data from that address. So let's hook up ALU result to the data memory. We're putting in 2000 as the address to the data memory. Data memory looks in there and it comes back with whatever value is at that address. Let's suppose the value happened to be 10. So now we'll put 10 on the read data bus. And finally, we need to write that value back to the register file. So let's add a wire bringing the data out of the data memory and back to the write data terminal of the register file. The address we want to write to is register 6, which was in bits 11 through 7 of the instruction. So let's hook up bits 11 through 7 of the instruction to the register file, and let's add a control signal called Reg Read. And we'll assert Reg Read, so the value 10 will be written to register 6 at the end of this clock cycle. And that completes what we need to do, almost completes what we need to do for load word. There's one more thing. Program counter is still at 1000. So we need to add 4 to the program counter so that we're pointing to the next instruction. So let's provide an adder that will take the current value of the program counter and 4, add them together. We'll call that PC plus 4, and we'll bring it around as PC next, the next value for the program counter. So 1000 plus 4 makes 1004, and on the next rising edge of the clock, we'll load 1004 into the program counter, so we'll be ready to do the next instruction. And that wraps up handling load word.